Okay, so I'm going to grab a pen. So what I want you to do is try those out, okay? Oh, actually, including answering how they are related. Once you're done, hit unpause and then write down the definition of limacons with an inner loop. So we have two equations, technically four, but I'm going to write two on here. We have A plus B sine of theta, or A minus B sine of theta. Then we have the same thing except cosine of theta. Now the difference between without a loop and with a loop is this. This is still the same. A and B are both positive, but because A is less than B, now it is with an inner loop, and this is super important here as well. The graph of a limacon with an inner loop does, okay, pass the pole twice, not just once, not never, but twice. Remember, without the inner loop does not ever touch the origin or the pole, but this one passes twice. Now let's go do example 1G. Even though this year you guys get to graph it using technology, but symmetry test, you are still on your own by hand, okay? So what I want you to do is test it out. Why don't you try it out on your own? Okay, again, I want you to try it out on your own, okay? Start with your polar axis. Write out the definition. What are you replacing? Then go on and do the line of theta equals pi over 2. Write out the formula, like same thing, right? And then do the pole. So we want to start with polar axis. Okay. Replace theta with negative theta to see if we get the same thing back. So r equals 1 minus 2 sine of a negative theta. Well, sine, it's an odd function, so it becomes 1 minus, which is originally, and then an odd function means you can take the negative in front of it, which gives us r equals 1 plus 2 sine of theta, which is not exactly the same as the original, so it's not symmetric about the polar axis. Then we can go to the line. Theta equals pi over 2. This is when we replace theta with or by pi minus theta. So r equals 1 minus 2 sine of pi minus theta. 1 minus 2 open bracket. The difference of signs, that's sine of pi times cosine of theta minus cosine of pi times sine of theta. No, bracket. All right, so r equals 1 minus 2 sine of pi, that's going to be 0. So I have negative cosine of pi. Cosine of pi is negative 1, so negative times a negative is now a positive sine of theta. Woo, woo. It's exactly the same. So right now it is definitely symmetric about the line of theta equals pi over 2. I would take my highlighter. I'm going to highlight this. The reason I want to highlight that is because when we graph it out using decimals, it should be reflected about the y equals axis, okay? Now, the last one, did I get the pen back? Nope, let's get the pen back. Okay, the last one is your pole, which we want to replace r with negative r, okay? Oh, immediately we know that's not going to happen, so we can just X that out right away, just like that. Now, we have our A value is 1, our B value is 2, and A is less than B, so we know for sure that this right here is a limacon with an inner loop, okay? Later, I will ask you to identify the curve, okay, or the shape of the curve, so make sure we know how to recognize the graph without actually having to graph it out. All right, let's bust out our decimals to see what this looks like. Let's, we have 1 minus 2 sine of theta, so let's X, no, actually, I don't want to X that out. I'm just going to change just that to 1. Okay, so as you can see, remember we talked about it looping around the center twice, and this is exactly what's happening, okay? And I'm going to identify 0. I have a mark at 2 units, so that's where I want to plot. So 0 is 2, just like that. Then I got pi over 2 is 0. Okay, so plot that. Pi over 2 is 0. Then what's next? Then I got pi is negative 2 there. Or pi is 2 units. Okay, so go back to my graph, just like that. Then what else? 3 pi over 2, 3 units. Okay, 3 pi over 2, 3 units. 1, 2, 3. So just like that. And what else do we have on the curve? Then we have 3 pi over 2 again at 1. That's like 1 unit. Okay, so 3 pi over 2 again at 1 unit. Just like that. Okay. So it's a limacon with an inner loop. Okay. So I'm folding this and I want to go. Ready? Start at here. How about this? If I get a different color pen, would that help you see it? So we start at 0, 2. Is that 0, 2? I want to double check one more time, okay? Oh no, 0, 0, 1. I lied. That's 0, 1. I'm sorry. The 2 is right there. So I lie on that one. 0, 1. And so is pi. Okay, so 0, 1 is right there. Okay. Let's double check one more time because I think I'm a little bit off. This is pi over pi is 1 again, 0 is 1, and then 3 pi over 2 is 1 and 3. Okay. So how does it touch the center twice? What we want to do is we want to start at 0 radians, 1 unit, and we go through the center the first time to draw the loop. Okay, that's 1 time going through the center. Then we loop this around. That's a 2nd time going through the center, as you can see right there. Okay, so that's how we, and then go all the way and then back to where we started, just like that. Okay, let's try that one more time so you can see how it looped twice. Okay, so we go, loop, ready? We start at the polar axis, loop through the center, loop right there, go all the way just like that. So that is a limacon with an inner loop, and my inner loop is pretty ugly, but that's how it touches the origin twice. So now we're moving on to this part. Go ahead and bust out your technology and graph it out. It's kind of fun. I like this one, so I think you'll enjoy this one as well. Once you're done, go ahead, unpause, and then let's define our definition for a rose. Okay, so it says here, rows, what are the equations? We get R equals A times cos of an n theta, and R equals A times sine of n theta, okay? And have graphs that are rose shape. If n is never 0 and it's even, the rose has 2n petals, okay? If n is neither positive or negative 1 and it's odd, the rose has just n petals. So hopefully, you guys on those ones right there, you knew right away that there were 3 and 9 petals, okay? And then up here, if n is even, just like those right there, then you know, if it's even number, then you know is twice. So that's 8 petals here and then 12 petals there. Okay, let's go to 1H. So again, we will do the symmetry test by hand. Okay, the first test is your symmetry with respect to polar axis. We will take out theta, replace that, replace theta with or by negative theta. So R equals 3 times sine of 4 times negative theta. This is immediately negative 3 times sine of positive 4 theta. Wah, wah, wah. Not symmetric to that. Then next we want to do the line of theta equals pi over 2. So replace theta with pi minus theta. So r equals 3 times sine of 4 times quantity pi minus theta. This is the same thing as saying 3 times sine quantity of 4 pi minus 4 theta, because then I need to bust out my difference of sine. So 3 bracket sine of 4 pi cosine of 4 theta, take away cosine of 4 pi sine of 4 theta. Okay, sine of 4 pi, that will disappear because that's 0. Cosine of 4 pi, that's going to be positive 1. So r equals 3 times negative sine of 4 theta. Because remember, this is positive 1, but this is a minus sign, so that stays still. Okay, so this is r equals negative 3 sine of 4 theta. Okay, again, not the same as the original. Currently, both of them are not symmetric. Last one is your pole. Oops. Okay, so the pole is replace r with negative r. Okay, so immediately, as you can see, none of this is working. Okay, none of this is working. So we know that this is a rose, okay, with 8 petals because n is even. Okay, n is 4. So rose with 8 petals. Our test says it's not symmetric to anything. So now let's bust out our Desmos in my case and see if our algebra is correct. Okay, so I want to keep sine, put in 3, and then let's do 4. Whoa, that's super pretty. And I have purple. That's even better. Let's do, is there pink in here? Whoa. Let's see, pink. Do they have pink? Nope. A red one, good. Okay, a red rose. That's pretty. Okay. So from graphing, doesn't it seem like it's totally symmetric? Not only that is symmetric, isn't it symmetric about the x-axis, the y-axis, the origin? So technically, isn't it symmetric with about everything? Okay, so why is our algebra incorrect? So remember earlier I said that the test that I gave you, it's 99%, right? Remember we talked about this? Or 90% that it works. So the 10% that it doesn't work, I remember you have to go and use that one formula about the pole. Okay, so do the pole again, but this time replace theta with pi plus theta. Okay, all right, let's check it out. I'm out of room right there, so I'm gonna go way all the way over here. So r equals 3 times sine of 4 pi plus 4 theta. R equals 3 bracket sine of 4 pi cosine 4 theta plus cosine of 4 pi times sine of 4 theta. And sine of 4 pi, that's 0, but cosine of 4 pi is now positive. So that's a positive sine of 4 theta. Whoa, it works. It is symmetric about the pole, okay? So I'm going to highlight this. Look at it, guys. It's totally symmetric about the pole. What does it mean by symmetric about the pole? That means it's an odd function. So whatever's in quad 1, it is immediately reflected to quad 3, and whatever's in quad 2, it's immediately reflected in quad number 4. So that's why you can see that it's symmetrical everywhere. So that's awesome. So now we know why there's that 10% that the first three formulas that we have been using the entire time doesn't work. So when that's the case, make sure you guys use this extra formula to make sure it works, okay? Now let's go and sketch it out. And let's see where those were first. And looks like we know we have 8 petals from our formula. So let's look at it again before I make my dots. So we got 2 in each quad. And the tip, okay, so the radius is 1, 2, 3, 4, 5. Wait, hold on. I keep counting one circle as 1 unit, but that's not true. The longest length is 3 units, okay? So, and it looks like it's 3 units, and I'm gonna try to see if I can make 8 dots and then just go from there. Okay, so let's go. I keep counting one circle is 1 unit in decimals, but that's not true. And this is going to be a, oh, I don't need a highlighter. This is a pi over 6, but I knew it was 1, 2, 1, 2, 3. So that's 1. And I knew, let's see what the second dot is. Right in front of pi over 6 and behind pi over 3 is the second dot. All right. So there you go. Oh! And so this is, guys, symmetric about everywhere. So I'm going to go over here and make a dot there. And then go over here and make a dot here. And go over here and make a dot here. Remember, it's symmetric about the pole. That means all the quads will look just like that. All right, do I have 8 dots? 2, 4, 6, 7. Nope, I need 1 more. All right, 8. All right, now make your rows. 1 petal, 2, 3. Oh, I totally missed out, dude. Oh, that was awesome. 3, 4, 5, 6, 7, and 8. That's not too bad by hand. So as you guys saw that we were able to graph that out using decimals. Remember, years past that we were not able to use technology to help us cheat, quote unquote, then this one was a bit more difficult to graph. Now, but what if we connect this polar equation to a rectangular, not rectangular, but to algebra 2 trig, right? So instead of using r and theta, what if we go and use y equals 3 sine of 4x? Well, if we use this, then as you know, we can start with the period. The period is 2 pi divided by b, which is 2 pi divided by 4, which reduces down to pi over 2. So what's that mean is that I'm going to be able to graph the entire full circle from 0 to pi over 2. But because we are connecting it with the polar, we will go all the way to 2 pi. That means I will be able to graph 4 full periods, okay? So this is a pi over 2, so that tells me that, hey, you know what? I'm going to graph the entire sine function from 0 to pi over 2. Let me get a new pen. You know what? Let me just make all the tick marks first. And for our equation, our amplitude is 3. So we will go up 3 and down 3, just like that. And every period has 4 equal quadrants. So we will put the tick marks in. Now, even going further, half of pi over 2 is going to be pi over 4. Half of pi over 4 is a pi over 8. So think of it as each tick mark is a pi over 8. Now, over here on our not unit circle, on our polar grid, this is going to be a pi over 6. This is a pi over 3, 2 pi over 3, 5 pi over 6. And then this is going to be 7 pi over 6. And this is 11 pi over 6. This is 0. Pi over 2, it's up here. Oh, look, I already wrote pi over 2 for the periods. Why don't I just use that as well? There you go. And then this is a pi. 3 pi over 2, just like that. Oh, and then I'm missing 4 pi over 3 and then 5 pi over 3. Okay. Now, because each tick mark on our x and y coordinate here, it equates to a pi over 8. So what I will also do is kind of make it a denominator of 8 for just the main ones. How about if I use a different color for that? We will go red. So a pi over this is 8 pi over 8, just like that. It's easier. And this is going to be 8, so 4 pi over 8, just like that. And then this is going to be, this is 8, so that's going to be multiplied by 4, so 12 pi over 8. And this can be back at, if it's 2 pi over 8, it's 2 pi, so that's going to be 16 pi over 8. So that way we can see it a little bit better, like when we transfer it over to the polar grid. Okay, so let's start with going, the amplitude is 3. So that means that my max is going to be 3 and my lowest is going to be -3. And signs start to 0. So we're going to go 3, 0, down 3, and back to 0. So as you can see, this is just one full period. But the polar grid has a full circle, so that's all the way to 2 pi. So I'm just going to continue the pattern. Okay, just like this. Now, if I miss a dot or a tick mark, hopefully I will be able to spot it and fix it. So let's continue this curve. It's not going to be a really perfect curve because I'm graphing by hand here, but this will help us connect it to the polar. Okay, all right, so that's from 0 to 2 pi. So as you can see, we have all of our petals here. The max, it's 3 units long, and the first one is at pi over 8. So pi over 8 is slightly smaller than pi over 3, so let's get a different color to graph out this beautiful rose. How about if I go and see, is there a purple? Let's try purple. That's fun, huh? All right, let's do that. Sounds good. Okay, so we will start with pi over 8 and 3 units. So 1, 2, 3. So let's guess that's right there. Okay, so that's pi over 8. Then if that's pi over 8 right here, 2 pi over 8 here, 3, 4. And this is 5 pi over 8, just like that. 6, 7, 8, 9 pi over 8 is here. So what if I just add a period? Okay, a period is 4 pi over 8. So the next one is going to be 13 pi over 8, just like that. Now, how about the bottom? On the bottom, I could also have these petals out. Remember, the amplitude, it's an absolute value. So these, even though on our graph is going downward at -3, but when we are graphing out an amplitude, we're just going to go opposite directions. So this one, let's see, 1, 2, 3. So it's 3 pi over 8. Okay, and then if I keep adding a period, 7 pi over 8 is here. Add 4 over 8, so that's 11 pi over 8. And then add 4 more, so that's 15 pi over 8. So these are all the locations of my longest, or the tip of the petal, I would say. All right, so 5 pi over 8 is slightly over here, and it's going to be just like that. Okay, so I just graphed that. 9 pi over 8, it's slightly past pi. So what if we go right there? Checked. Okay, 13 pi over 8 is slightly past 3 pi over 2, so that one's right there. Check. Now we can use the symmetry, because remember we tested for symmetry earlier, and then reflect all these dots. Or just for the sake of demonstration, I'm gonna go and make a dot at 3 pi over 8, and 3 pi over 8 slightly to the right side of 4 pi over 8 there. 7 pi over 8 is above pi, so check that off. 11 pi over 8 is to the left of 3 pi over 2, and then we got the last one, 15 pi over 8, which is over here. Okay, so those are the dots, and remember this is by hand, so I'm just gonna try my best to sketch that out. So just like that, those are the tips. So that's the connection between our x and y coordinate and our polar. Now this one looks, if we were sketching it out in x and y coordinate, it's slightly easier to kind of translate that to polar grid, but they're totally related. That's why we can go back and forth. All right, guys, we have one last definition here. It's the lemniscates. And the equation for lemniscate is the unique one. It's the only one with r squared. So r squared equals a squared times sine of a double angle, or we can have cosine. So again, lemniscate is the only one with r squared here. So r squared equals a squared times cosine of a double. So now let's go and graph out one eye. Okay, just like the other ones, you are to do the symmetric test all on your own without a calculator. Okay, so go ahead and test it out for me. You have 3 tests to try, and I want to see how far you can go. Okay, so hopefully you started with the polar axis, or any of the ones. It doesn't have to be with polar axis, okay? So if you started with the polar axis, you will replace theta with negative theta. So r squared equals 4 times cosine of 2 times negative angle. Remember, cosine is an even function. So an even function meaning that the negative can just completely disappear. Oops, I forgot the 2. All right, so immediately we know that works. So we will highlight it, okay? And then we will go check the other one to see if the other ones will also work. Next, I want to go to the pole or the line. It doesn't really matter, guys. So for the pole, you could replace r with negative r. So negative r quantity squared equals 4 times cosine of 2 theta. Okay, so negative r quantity squared, that's definitely going to be the same. So we know it works. R squared equals 4 times cosine of a double angle. That works as well. Highlight that. Okay, one more test. Whoops. Our last test is going to be the pole. Wait, we did the pole already. So we want to now go do the line. Sorry, I kind of did out of order this time. So the line is to replace theta with pi minus theta. Okay, so r squared equals 4 times cosine of 2 times pi minus theta. And distribute that to r squared equals 4 times cosine of 2 pi minus 2 theta. Let's use the difference of cosine. So for bracket, cosine of 2 pi, cosine of 2 theta, minus sine of 2 pi, sine of 2 theta. Okay, so cosine of 2 pi, that's going to be 1. So r squared equals 4 times 1 times cosine of a double maintains that a cosine of a double. Sine of 2 pi is 0, so that will go away. And so this also works. So all 3 of them works. Okay, so it is symmetric with respect to all 3. Okay, the line, oh, you know, I forget, line of theta equals pi over 2. Okay, so all of them works. Okay, so now we have to go and graph it on our decimals, right? Oh, before I go and graph it on a decimal, let's identify the graph. Okay, this is a lemniscate. Okay, so lemniscate is like a propeller. So this is a lemniscate. Let's go and graph it out. And I'm going to find my decimals. Where is that? There you go. Okay, so as you can see, I already typed it in for you, but oh my goodness, it's not graphing. There's nothing on the curve, right? So if you want me to type it in again, I could do that again. So r squared, there you go, equals, and you have 4 times cosine of 2 theta, double angle. Nothing comes up. And the reason nothing comes up is because that it doesn't recognize r squared. So we have to go and solve for r. R equals, now we do a square root, so there's a square root down here. Everything's under 4 cosine of 2 theta. Okay, just like that. Now, normally, when we take a square root, we write plus or minus. But the unique thing about polar coordinates is that the radius is exactly the same whether you have positive or negative. And let me graph another one out for you. What if I do r equals negative? Well, in polar coordinates, we can get the same graph, right? Negative radius is just saying that we are going to the opposite direction. But we can always get to the same spot having a different angle as long as we can always, I'm trying to type theta. There you go. So whether I put positive or negative, they're exactly the same. So in polar, negative radius is just really saying that we have directional. And it doesn't really matter because as we have done a few homework questions where I can get to the same exact polar coordinates by going a different angle or having negative radius or positive radius, right? We can always get to that same exact spot. So that's why in polar, when you take a square root, it's not necessary needing the plus or minus to graph it out, okay? So we can sketch. It looks like we have 2 radius, okay? It's on 0 radians and pi radians, okay? Let's, what? There you go. 1 and 2, whoa, what's that? There you go. And I'm probably gonna have to fold my computer back here to sketch out this propeller. Just like that. So for this example, we have one last one, and this is definitely all calculator. You can't really do e to a power of some angle without one. So I will now find my calculator one more time. Okay, let's find my decimals one more time and graph that. So we want to graph out r equals e. Let's find where that is. So to find e, just type e on your keyboard, okay? And then to the caret to the power of, let's see, that was theta divided by 4. So theta divided by 4, just like that. Okay, so as you can see, theta is in between 0 and 12 pi. So what does this look like? It looks like it keeps going and going and going. Look at that, it's a spiral, right? So the more I zoom out, okay, the more spirals that you will see. So for this one, let me zoom. I just want to sketch a couple of spirals, and we can go and go back to my paper. Here's my paper. Okay. Okay, from the graphing, we know it's not symmetric to anything. So symmetry test, by now we can do it manually, and we're going to teach a little bit. It's not symmetric to anything, so we're going to say it's none, and it is called a spiral. Okay, the shape is called spiral. And if we really want to, we can make a table, okay, just to get a value. When x, there's no x, I'm sorry, there's angle and there's radius. When the angle is 0, e to the 0 is always 1. So at 0, I have 1 radius, just like that. And if we want to make a table, we keep on doing that. But just to kind of speed things up, I'll give you a few more just to get an idea, okay? At pi over 2, I'm using my calculator here. I'm going to cheat a little bit. E to the pi over 2 divided by 4 is about 1.5. At pi, again, I'm using the calculator. I don't have any magic here. It's about 2.2. And then just 3 pi over 2, it's about 3.2. That will give us enough to graph it out. So pi over 2, 1.5, pi, 1, 2, 2.2, 3 pi over 2, it's 1, 2, 3, 3.2. I can also go negative, okay? If I go negative pi over 2, it's about 0.7. If I go negative pi, it's about 0.5. If I go negative 3 pi over 2, it's about 0.31. And again, I'm using a calculator here. So what does that mean? So 0.7, it's right here. If I go here to here, right? And then half, it's right there. And 3 pi over 2 is like closer and closer. As you can see, it's getting closer and closer to the pole. Just that I don't think it's ever going to reach the pole. And it looks like that. Oh, that's some ugly spiral. Man, I can't graph for the life of me, huh? Oh, still ugly. Sorry, that's as best as I can do with that with the spiral. Now I put on here, if you have time, you can try it out, but you don't have to. This is actually something super cool to try. Can you see that if we are using the Rose formula and your n value is this k divided by d, so if I go 7, so n equals 7 and divided by, let's just say what looks cool. Oh, this one looks cool. 8, okay, so 7, 8. Is my n. So if you enter in r equals, let's pick an a value of 5. That's just how the radius is. Cosine of 7 over 8 theta. It should give you a pretty cool graph to kind of try out. I love this one because it's kind of easy to mess around with. Okay, so r equals, let's say 5 cosine of 7 divided by 8, we said, and then theta. Ooh. Look at that. That's super not cool. Okay. And you can keep on going, right? So how about if we go to 14 pi or 20 pi? Okay, pi, there you go. So the more revolution that you guys graph, the more lines or the more drawing that's going to be. What if I go 100 pi? Okay. So again, so get to the point where it does a complete cycle. So that looks cool. Let's try out the shapes.